So now let's calculate the damage for this, for one repetition. Now I'm just going to copy this to at the top here to simplify my calculations. I need this. This is the stress spectrum. So I take the stress spectrum, and because I want to do it row for you, so that you can see how it works. So that's what we had. We had that table there. Now, the first thing that we need to do is, we already have the SN curve that takes into account all the factors that are applicable. What we need, and the SN curve is given by this equation, but we first need to calculate, our step one will be here, calculate the equivalent completely reversed stress amplitude from modified Goodman mean stress correction is, this is our equation, Control C. Now let's look at the first line. Now let's call it a name. So this is alt nu EA. This is for sigma A equal to 100. MPA, sigma mean equal to 200 MPA, and NI equal to, NI, that's the number of cycles, equal to 10,000 cycles. That's the one that we have, and what we're going to have here is sigma AR. In this case, will be equal to, the amplitude that we had was 100. 1 minus the mean that we had in this case was 200. And the ultimate tensile strength is 1050 MPa. 1050 MPa. And that, if we calculate this, is equal to, open my MATLAB. So I'm going to take here. So here we have 100 divided by 1 minus 200 divided by 1050. That's the equation that we have. So let's call this sigma AR, just so that I can find it easily. Sigma AR is equal to that. That's the mean stress corrected 123 MPa. Where's my MATLAB again? Let's make this window a little bit, because we're going to do a lot of calculations now. Let's take this window, this Microsoft window, and move it up a little bit so that we have space here at the bottom for our MATLAB on our recording. So there we have that one, and let's put our MATLAB there right at the bottom. So let's put MATLAB right there, and then we can easily switch between the two. So this is 123.5 MPa, right? That's a completely reversed stress amplitude. Because we had a tensile mean stress, we expect the amplitude to increase from 100 to a larger value, right? So I'm just going to say here, Goodman mean stress correction, to make this easy. And then we're going to calculate the fatigue endurance, the endurance or fatigue life for 50%. No, it's already modified. So we're going to calculate the fatigue life. And that is equal to, the equation that we need to use now is this one here. Copy. Let's copy this into here. And in this case, it will be equal to, now in this case, our stress is larger than the endurance limit. So here we will have it equal to this equation here, Control C, Control V, and sigma IR here at the bottom will be 123.5 MPa. And if I calculate this, I get a fatigue life of, now let's calculate fatigue life here. So it's 80.4. So I can say here NR is equal to 80.4 divided by 123.5, right, to the power 4.35 times 1 million cycles. And we get there and we see it's 150, let's say format long G, and then we have NR is equal to 154,565. 154,565 cycles. 154,565 cycles. And now I can calculate the damage. The damage by this. So DI is equal, the damage is equal, DI is equal to the number of cycles I divided by the endurance limit I, or fatigue life I, from the SN curve for the applicable probability of survival. And in this case, we had 10,000 cycles, so this becomes equal to 10,000. Let's first put the division, it's faster. So this is 10,000 divided by 154,565. And that, if I calculate it, is equal to my MATLAB. D1 is equal to 10,000 divided by 545,565. And that's 0.01833. That's enough decimal points, I would say. So that's the damage caused by this repetition. Now we're going to do the next one. And the next one will be 50,005,000. So I'm going to copy this to the bottom. Control C. Now let's do the next one. So the next one will be 50,005,000. Let's make this yellow so that it stands out, so that we know what we were doing. So this was this one. 50, 0. So this will become 50. 50, and this will become 0 mean. 0 mean, it was 5,000 cycles. Right, now let's see. Our equation here, firstly, will change to our stress amplitude. It's 50. It's 50 divided by 0 over there, so it's 50 over 1. So we will stay here again with the 50 MPa. We expected that, right, because that's already a completely reversed stress amplitude. Here, this 50 MPa is below 80.4 MPa. So in this case, we will have an endurance of infinity. Right? So that's the fatigue life that we will have at 50 MPa, infinite life. That comes from the SN curve, already modified for probability of survival and already modified for temperature and all these other things that we have. That's the SN curve for this, the exposure that this specimen will see. So in this case, we will have 5,000 divided by infinity. Infinity, and that is equal to 0. So that specific stress, completely reverse stress amplitude of 50 MPa will do no damage. It will give infinite life. Remember, we don't look here at ultra high or very high cycle fatigue. We just look at the stress life up to 1 million cycles. That's where we modeled the SN curve. Let's look at the 120,000. So let's copy this down. So now we have Control C, Control V. It's a frustration. I don't know where this, oh, there's maybe a page breaking. So we have 50, here we have 100, if I remember correctly, 100 and 100 MPa. Let's make sure. It's 120,000. 120,000, 20,000 cycles that we have here. So here we will have 100, and we will have 100, and we will have 20,000. But why does this sound so familiar to me? Oh, this was 200 MPa. So this one, and that was 50 MPa, and now we're with 100, 100. Okay, 100, 100. Now let's calculate the sigma AR. Sigma AR will be equal to, in this case, equal to 100 minus 100 over 1050. That's 110.5 MPa. So this comes out to 110.5 MPa. Now in this case, 110.5 MPa is larger than the endurance limit of 80.4. So in this case, we will use this equation here, Control C, and this is the equation that will be applicable here. So here we will put in 110.5 MPa, and we will calculate this. Now in this case, we're going to use NR here again. NR is equal to, I want to use the equation. So this will be 110.5. Same equation, and NR works out 250,748. 250,748 cycles. That's the endurance that we calculate at that stress, completely reverse stress amplitude. And now we can apply it here. So this will become 20,000. And there at the bottom we will have 250,748 cycles. And if I calculate D, so D2 in this case was equal to 0. And if I now calculate D3 in this case is equal to 20,000 divided by 250,748, right? And that's equal to 0.079796. How many decimal points did I use? 1, 2, 3, 4, 5. So this works out 0.07976. Right. So that's what the damage is that we calculate in this case. Let's call this D3 because that's the third damage that we want to calculate. So D3, sorry, I'm going to keep that DI. That's a general equation. And I'm just going to put here D3. D3 is equal to this. So that's D3, and we'll do the D2 and everything there at the top there as well. So this is D2 is equal to this. And here we will have D1. D1 is equal to this. Right, so D1, D2, D3 that we have. And now let's go to the last one. The last one is a 200 minus 100, 2,000. Here we have a 200 minus 100, 2,000 cycles. So here we have amplitude of 200, a mean stress of minus 100. Now let's calculate sigma AR here. Sigma AR will, in this case, will be 200 amplitude, and it will be minus 100 for the mean. And we calculate the 182.6 MPa. That is the, and now we can see the completely reverse stress amplitude is less than the applied amplitude. Why? Because of the compressive mean stress. Compressive mean stress is beneficial. This completely reverse stress amplitude is larger than the endurance limit. So we need to apply this equation here. So this equation here becomes that, and we put in here 102.6 MPa. And let's calculate the endurance or the fatigue life at that stress range for 1% probability of failure. In axial loading, 102.6. And if I calculate this, I get this equal to 28205. So this will become 28205 cycles. I always use the slightly less cycles. I don't normally round here, but it doesn't really have a big difference. So this will be D4, and D4 will be equal to 2000 divided by 28205 cycles. And let's calculate D4. Let's take D3 and D2 and D3. So there was D3 calculated. And let's say Control V, let's put this D4. D4 now is equal to 2000 divided by 28205 cycles, and that's equal to 0.0709 0.0709. That's what the value will be. And now let's do the total damage. Let's put the heading 4 in here. Let's calculate the total damage. Remember, that is for the duration of the stress spectrum, and the stress spectrum was for 1 repetition. The total damage, according to the Palmgren minor rule, is alt nu EI. The total damage is equal to the sum of all your damages, the sum of your individual damages, which we also know is equal to the sum of your NI, the number of applied cycles divided by the fatigue life at that stress, applicable stress, completely reversed stress amplitude. And in this case, it will be equal to D1. It will be equal to D1 plus D2 plus D3 plus D4. Sorry. And that is equal to, now D1, I've calculated it. D1 was here 0.0183 plus D2 was 0 plus D3 was equal to 0.0798 plus D4 0.0709, and that is equal to, I'm just going to calculate them up here, 0.0183 plus 0.0798 plus 0.0709. That's what we have. The total damage is 0.169. Let's do a quick test here. D1 plus D2 plus D3 plus D4. How much is that? Yeah, that sounds right. Okay, so that is our total damage per repetition. Total damage per repetition. Now we can calculate the number of repetitions to failure. the number of repetitions to failure is then alt nu EI BF equal to 1, BF equal to 1 over the total damage, and that's equal to 1 divided by 0.169, and that is equal to 1 divided by 0.169 is equal to 5.9. Is 5.9 repetitions to failure. That's the number of repetitions that we can have is then 5.9 as calculated below. So there we've answered the question of this problem. What was the question of this problem? The question of this problem was as follows. That was the problem statement. Then our solution, we calculated the SN curve for the notched specimen, and they wanted to know what is the fatigue life of the component for a probability of survival of 99%. Here we went through the whole process. We calculated the modification factors. We had an equation for the SN curve. Then we did the damage for 1 repetition. And we saw the damage for 1 repetition was equal to 0.169. And the number of repetitions to failure is 5.9. So now we can write down the conclusion. Or answer the question that they wanted. The fatigue life of the component for 99% probability of survival is 5.9 repetitions. Now, if they said the stress spectrum was in terms of years, it would have been 5.9 years. But that you know.